One common use for capacitors is as a temporary energy source during switching operations. To help understand this capacitor application, we'll look at a similar system that stores fluid energy. An important use for capacitors is as a temporary energy source during sudden power demands. For example, we have a device here that's connected to an electrical circuit. The device intermittently demands power as a result of this switching operation. When the switch is open, the load doesn't require any energy. But when the switch closes, there's a sudden demand for energy by the load. This can be a problem since it takes time for the source to respond to the energy demand, especially if the source is far away from the load. We can fix the problem by adding a capacitor near the switch. Now, when the switch closes, the capacitor can provide power while the voltage source is catching up with the demand. When the switch opens again, the voltage source can recharge the capacitor so that it'll be ready for the next time the switch closes. Before I introduce a corresponding fluid system, let's talk about a fluid version of the capacitor itself. Devices called accumulators store liquid and are pressurized by a gas. The plenum under my stairs that keeps the pump from cycling on and off is a bladder accumulator. This is a picture of that kind of accumulator. The liquid is shown in yellow and the gas in blue. The gas is inside of a flexible bag. Energy is stored by compressing the gas. Liquid can enter or leave the accumulator here. When the pressure is high at this inlet, fluid enters the accumulator and compresses the gas, allowing the accumulator to store fluid. If the fluid pressure here drops, the gas expands and forces fluid out of the accumulator. The accumulator stores fluid in the same way that capacitors store charge. One example of a capacitor-like device is the tank on the back of a toilet. The water line won't directly provide enough water to flush the toilet, so we store water in the toilet tank to flush the toilet. After we flush, the energy gets replaced when the toilet tank slowly fills up again. My water's pumped out of a well. It's bad for your pump to turn it on and off every time you open a faucet to get a glass of water. The tank has an air bubble. When the pump goes on, the water enters this tank, which compresses the air bubble. When the pressure in the tank gets high enough, the pump turns off again. As I use water, the air bubble expands, releasing the stored energy. This fluid system is analogous to this switched electrical system that I showed you previously. There's a reservoir or a tank here that provides fluid to the system. It corresponds to the power source in the electrical system. There's a long pipe that provides fluid to a pump. The pump is like our load. When the pump turns on, it suddenly demands fluid flow. The line here keeps the reservoir from providing fluid immediately, so the pressure at the inlet of the pump drops. If the pump inlet pressure drops too much, we get what is called cavitation in the pump. During cavitation, bubbles form on the pump impeller. When these bubbles collapse, they create very large pressures, which can pit and erode the pump impeller. This picture shows the result of cavitation, something we definitely want to avoid. We can keep the pump from cavitating by adding an accumulator at the pump inlet. This can make up the flow that we're not getting from the reservoir while the inertia in this line catches up. Once we turn off the pump, the reservoir will replenish the fluid that the accumulator lost when we started the pump. Now let's talk a little bit about the math associated with modeling the electrical system and its analogous fluid system. This electrical system, where we have to include a capacitor to provide supplemental power during a switching operation, works the same way as this fluid system, where the accumulator temporarily provides fluid when we turn on the pump. It's sort of cool that we can use a similar fluid system to understand how the electrical system works. But the best part is that these systems are more than just similar. If we mathematically model them, they're actually identical. The only difference is that the variables change names. Fluid pressure corresponds to voltage in the electrical system, and current in the electrical system has the same role as fluid flow rate. This means that the same math tools transfer directly between engineering disciplines. If you can analyze an electrical system, you should be able to analyze fluid, thermal, and mechanical systems. One engineer I used to work with would include springs, masses, capacitors, and inductors to fluid system diagrams. It didn't matter which symbol he used as long as the math was the same.